another digit that I don't remember. It was 1, I think. Yeah, I think let's decide that it's 1 because I will not be able to stop it in the right place. And yeah, let's decide that it's 1. So I take these 3 bits and add to it 1 new bit from the leftmost side. So what do I do with this part? Moving from here to here, I need to get rid of this 1, if there is 1. If it was 0, I didn't have to subtract everything. So subtract t of s plus 1 times 1. Divide by 2. Add, look at the bit that is just now added from the left. If it is 1, then you're adding it to t of s. That is, I look at t of 8, and I want to generate from it t of 9. No, generate from t of s, I want to generate t of s plus 1. So if the new bit that is come from the left is 1, I'll add the value of 1 times 2 to the m minus 1. That was, if I have 4 bits, this number is the 8 that came from the left. Okay? Everybody's cool with this? That's just the formula, meaning it at a constant time, supposedly in constant time, I can compute from t of s what is t of s plus 1. Remember what we are competing against. Naive algorithm runs in order m times n. What we want to get from it is n will be the dominant part, m is much larger, but we want to get linear time algorithm. Okay, everybody feels comfortable with this formula? And yeah, so three arithmetic operations. So it looks like I can compute the new value in constant time. All happy. And of course, after I take t of s, I'll ask is t of s equals to small p. What is small p? You can guess it's the number that represented by the string p. P was a pattern. Think about it as a binary string. It represents some number. So just to compute from for every s, compute t of s from t of s minus 1. It takes constant times, 3 arithmetic operations, and compare it if it meets the pattern or not. If yes, then you're reporting fit, and it looks like we are done. Or are we? Or who can argue what's the problem here? Either virtual people, real people. If anybody of you sees a bug, or it's yeah.
Comparing, how can we compare? We can compare it with like m times, or we can do it using hashing in constant time.
Well, so far, this was just a number, a value. P is just a value. I did just a binary representation of the pattern. These are two numbers. I called a compare operation.
Yes, the compare operation, if we do as a string, then we have to
check one, yes. But since it's a number, it looks like it's constant because we usually compare, and I don't need the hashing so far. I mean, I'll need the hashing, but first we need to express what the issue with this algorithm.
The value of ds may be exponentially large if m is
excellent. If m is m bits number, I mean, let's ignore the issue from moving from ASCII to moving to binary representation. I look at the bits individually of the ASCII character of the to be or not to be. This is, even if the pattern is just this one, you're talking about a string of, here it's only 16 bits, 2 characters, but it's very easy to get more than 32 or 64, whatever your computer word is. But the number of bits in M might be way, way larger than one computer word. So the compare operation doesn't take constant time. Your language, depending which one, might complain when you try to multiply such a large number. You cannot even store it in a normal computer word, not even if it's long. You can use a floating point, but then it's not really the number, it's approximation, so that doesn't work. But it's still a very good start. Because from now on, where am I going? We will store I will not compare instead of we look at the two hash values of both these numbers, T of S and P, and I'll ask, is the hash values match? And if it's rare enough that it match, then I can say there is a chance of false positive, of course. There is a chance of false positive, obviously. The hash values are the same, but the keys, the hash values are the same, but the numbers are different. But I'll try to control the chance that this happens. So of course, in this algorithm, once I see that the hash function match, that the hash values match, I'll have to check if the strings actually match or not. I'll have to verify it. But the algorithm is efficient just if I'll say that the number of false positives will be small. Okay, so that's one challenge, but to control the number of false positives. And there is one challenge coming sooner, that is, if I don't really want to keep T of S, it takes too many computer words. I don't really want to multiply it by 2. As is, it takes too many computer words. It's a number, but it's a number doesn't make it something that I can stack into one computer word. So, as you noted, we need to perform each operation in constant time if we want linear algorithm, but it's usually doesn't work if the number of bits is more than 64. Okay. here I just wrote in a lot of words that I can divide when I'm living over a finite field using a group. If I think about all the numbers modulo a prime, and it is a prime, then for every number, integer, between 1 and m, between 1 and m minus 1, it has an inverse. It has x minus 1. That is, literally I can perform division. That is, x minus 1, it means that I'll take x and I'll multiply by y. Modulo q, it will be 1. Quick example and refreshment, it's also good for the midterm, to remind you what the basic mechanisms that we used again and again. I think about some number a between 1 and 5. So a between 1 and between 1 and 5, because I want to work in modulo 5. And I'm looking at the number xa mod 5. 5 is a prime. Let's try all the numbers. Proof by example. Let's try all the numbers where x equal 1, 2, 3, 4, and 5, of course, which is 0. And let's decide that a equals 2 in our little example. And what happens? 1 times 2 ax mod 5. If x is 1, then it's in on inverse. Nothing happens because of the modulo. And then 2x will be 2. 2 times 2 modulo m equals 4. 3 times 2 equals 6. Modulo 5 equals 1, meaning that the inverse of 2 is 3 and vice versa. And 4 times 2 is 8. Modulo 5 give me 3. And of course 0 takes me to 0. So what am I trying to show you? Each one of the numbers, no matter what is a, each one of the numbers appears exactly 1, the numbers between 1 and 5. Meaning that no matter what is a, one of these numbers will be the inverse of a. A is 2, then in this case x, the inverse of a, will be when do I get 1? 3. And we actually used this lemma quite a few times when we talked about universality. Said, as long as we are leaving everything under a prime, or I'm only playing with numbers that are smaller than this prime, then this sequence of operations, well, this function by itself, by the way, I can make it a universal family of hash function, another hint for the meter. I can argue that all these numbers are different, and so on. Great. What does it tell me? It tells me that in the operation of creating a, and I also want to remind you that we talked about this fact multiple times. If I have two numbers and I want to sum them and it's too large to my taste, I can take the first number, compute modulo q, and take the second number, compare modulo q, and of course do one modulo q at the end. But if I have a multiplication of a numbers, like in the case of dot product, we use this fact multiple times. So from now on, T prime of S, did I skip the definition? T prime of S, if I didn't write it. what will be my hash function? Very simple, deliberately very simple hash function. Age of x is nothing but x mod q, and q is a prime. And notations, Ts was a number, Ts was just the number 101, the string 110, etc. The binary number, the number that is represented, that I wrote it in binary, and T prime of S. The prime is just my shorthand to say that's age of T of S. Take this number and compute it modulo Q. And similarly, P prime, you guessed, it's just age of P. So P prime of S is just this binary number modulo Q. How can I generate from it T prime of S? I'll subtract from T prime of S. I'll subtract 1 or 0, depending on what is this bit, just as I did before the modulo. And now I need to divide it by 2. How can I divide it by 2 if I want to only work with integers? I'll multiply it by 2 to the minus 1 modulo Q. We said that 2 has an inverse, like any number here. It has an inverse, I'll call it 2 to the minus 1. So I'll multiply it by one number, which I will just compute once and I know what it is. But 2 to the minus 1 modulo Q. That's just a division. Now I need to add to it T to the S plus M plus 1, that is a new bit that is joining, times 2 to the M minus 1, being added, and I'm computing modulo Q of the whole thing, but I don't really want to keep this number, 2 to the M minus 1 by itself is already too large. It takes too many bits. It's not a computer word. I'll just add to it 2 to the M minus 1, just do immediately mod Q. And that's a number between 0 and Q. And oh, by the way, I'll make sure that Q is a small number. Small, like less than 64 bits. So I know what is this number. It's a constant. I know what is this number. It's a constant. I am looking at 2 bits, do this multiplication, all under modulo Q. Take one more modulo Q just to make sure, and we are all done. That concludes this part of the algorithm. From now on, I'm just looking for moments where T prime of S equal P prime. That's a hash function, they're equal, and if they are, I check character by character, do they meet or not. So this part of the algorithm is very simple, very straightforward. Questions about it? Everybody understand why it's only 64 bits that I'm using and not M bits? So that answers the question, why do I need the hash value? Okay. So, and the problems are, of course, false positive. It could be that the strings don't match, but the hashed values, denoted by the numbers with tags, with prime. The hash values do match, so we need to use a random prime. And there will be some rules about what is this random prime. And the way that we're going to use it is, well, to my taste, it's extremely cool. Okay, we will show that the probability of a false positive is small, so even when I'll say, similar to the linear programming, if you wish, even if I'll say some bad things happen, I'm always checking when I see that this equals this, then I need to do like the linear, solved linear programming in 1D, or the rehash that we used in the closest pair. I'm spending a lot of time if bad things happen to check if there is this really a match or it's not a match, but I want to argue that I don't need to match this part multiple times. Okay, so let's try to understand better what happens if I have false positive. False positive will mean that T of S, the number after shifting the window to the S place, shifting the window by S, this number shifted by S is different than P, because if the number before the hashing are equal, that definitely means that it is a match. It's a correct match. But false matching will be when these guys are different, yet when I'll add the primes here and here, they will be different. Modulo Q, they are different. So let's understand how it happens. So I know that both this number modulo Q that these numbers by themselves, before the modulo Q, these numbers lives between 0 and 2 to the m minus 1. Why? Because I just used m minus 1 bits. No much smarter about it. So, question, how many primes can you find such that T of S modulo Q equals P modulo Q? How many different primes Q could I find that will cause this false matching? But if Q of S modulo Q, which is different than P, is different than P modulo Q, that will imply that move P to the other side, subtract P from both sides. You can do it under modulo. T of S minus P is equal 0 modulo Q. How can I have a number equal 0 modulo Q? Why does it happen that 12 modulo Q, and I'll tell you that Q is prime, equals congruent to 0? What can you tell me about Q in this case? The Q, the 12 is divisible, I think. What? It's English question, so I'm not sure. We want to say the 12 is divisible by Q, and Q is a prime. So what can you tell me about Q in this case? It could be either, Q will be either 2 or 3, because that's the only primes that divide 12. But if I pick Q to be 5, it doesn't work. Proof by example, once again. So how many primes do I have such that X equals, that is T of S minus P, which are smaller than 2 to the m, are divided by this prime? From this point, it's, for me at least, it was new material. So, and new ideas. So I want to ask, how many bad primes are there that will cause a false positive for these particular numbers? So to understand how likely it is to stumble upon such false positive, we need to understand the prime factorization of X over here. So what are prime factorization? To remind you all, I can take any number, 12 for example, and write it as 1 prime times another prime times another prime times another prime until you get this number. And obviously this factorization is unique to the order that you're doing it. And if you are using the same number more than once, then you can write it as a prime to the power of something, exponent of something, times another prime to the power of something. And this decomposition is unique. Obviously, for the X, the primes that divide it are unique. And take X and divide by the first prime, the smallest prime, you can continue and generate zero sequence. So X can always be written as 1 prime to the power of some exponent times another prime to the power of some exponent. The exponents are all integers, all the way until the last prime. Quick example, 12 equals 2 to the 2 times 3. 900 is 2 to the 2 times 3 to the 2 times 5 to the 2. Check. And 24 is just 1 prime that appears multiple times, appears 10 times.
Isn't EI much larger than 0, not 1?
EI is, no, 1 prime can appear by itself. That's the exponent. The prime should be indeed larger than 2. Excellent point. You see where it's going. But the prime should be, of course, larger than 2. But the exponent here, when I write 12, 3 appears once. So E1 is, 1 is fine. And each one of the pi's are larger than 2. Only primes that are larger than 2 are in the game. So now let's put this fact together. X calls me a false positive. X modulo Q gave me a false positive, meaning it's divided by one of the bad primes with respect to this X, or with respect to this theory. How many primes participate in the prime decomposition of X? Well, X, we already established it, X only have m bits, so X is smaller than this number. It's most 2 to the m minus 1. Now, I write X in this way. Each pi is either 2 or larger than 2. It's 2 to the power of something. If it appears more than once, better for me. But if X is 1024, it just means there is only one prime that divides this number. So if I pick Q at random, it's even less likely that it happens to be 2. The more primes that participate in this decomposition, the more likely it is for me to pick, by mistake, a wrong one, which will cause the module to be 0, which will cause false positive. Okay, so how many primes can I have? What is the largest value of k that I might generate, since each prime is larger than 2? And the exponents only help me. Then k here is, sorry, then k is not larger than m. Then I cannot have more than m bit. If I look at how many bits there are in the pattern, the number of primes that cause the false positive, is smaller than the number of bits that participate in the pattern. Okay, everybody is cool with this observation? It's important for where it's going. So I'll describe the algorithm like as if I'm really performing all these operations. We will actually replace the first part with a much simpler part. So as our next attempt, let's generate a set that, to be consistent with the book, I'll use capital prime to denote this set. And this set contains a lot of primes, 2 times n times m many primes. And each one of them is a relatively small prime. Small, like less than 2 to the 60. Small than log of m. Presumably you can store m, and n in your memory, meaning that you can give an address to each character of there, meaning that it's less than 2 to the length of the text is less than 2 to the 64. In other words, you can, each prime here is something that you can store in your computer world, in a single computer world. Okay, so imagine that I create such a set of primes. Well, what I'll replace it with, just a promo, what I'll replace it with is just pick a number or a prime at random, and with good chance it will do just well. But to understand why the algorithm works, we need to think about conceptually this set pi that will include, say, 2, includes 3, 5, 11, pj, q, j, ql, running out of indices, but pi is a set of Again, when I'm going to go with this is that I'm going to pick a prime out of pi. And all the primes are primes that I'm willing to work with. Don't have too many bits. And again, where it's going to be practically, since I'm just picking the prime at random, I might as well think about a database of primes and just say that's the largest prime that I'm willing to work with. Or I'll pick a number at random and check if this number is prime or not. That's another way to approach it, instead of actually having to have in my computer all this list of primes. But for the analysis, let's assume that I actually took my time and created pi explicitly. And now from prime, I pick from pi, I pick a prime q at random, and I run my algorithm. And I ask, when I'm picking q at random, how many false positive could I have, might happen? And possibly the answer is many. Maybe the input is designed so viciously such that there are a lot of false positives, but actually what I want to, and in this case probably you want to just repeat the experiment and pick another prime. You see that it takes too much, something bad with your data. Not bad, but there is some structures that you didn't notice. Just pick another prime. What I want to say is that there is a 50% chance that your prime will work very well. Will not have any false positive. Again, there is a 50% chance that your prime will not have any false positive. Why this? And the 2 right here is important. That will be where the proof is getting. So I'm looking at t of 0, the window where it was original. T of 0 is a number, very large number, but it's a number. P is a number that's going to be the state. P, I remind you, is just a number that capital P, the string, represents. It's a binary number. So t of 0 minus p, if it is divisible, if this number modulo q is 0, I'm in trouble. It's a false positive. Assuming, of course, that this is not a match, then it will be a false positive if I pick the q that divides it. So how many primes participates in the prime decomposition of this number? I look at the prime decomposition of this number. Of course, I don't do it algorithmically, just as part of the proof. I look at the prime decomposition of this number. How many primes participate in this number, in the prime decomposition? At most n. We saw it in the previous slide. There are k primes that participate in this number, and k is less than n. Again, why? Because each one of the prime is 2, and the maximum value of this number is 2 to the n. So I cannot have more than n primes. Each one is larger than 2, whose product generates this number. So I'm looking at t of s minus 1, and I'll say here are the primes, bad primes for t0. I just marked the primes that are bad primes for t0. See how did I for the proof I switch the rules. I said I first generated all these numbers and then I pick q. That's not how the algorithm works, but conceptually let's assume that I'm doing it. I generated all these numbers and then I pick q at random. So here are all the primes that participate in the prime decomposition of t of s minus p. And we said that there are at most n guys here that I just marked in red. Similarly, I'll move to T1. The next shifted the window a bit. Here are the bad primes. bed for t of t. Sorry, this was z for t1 minus p, and here I forgot the t0 minus p. t1 minus p. If we divide this number, so modulo it will be 0, that is t of 0 mod q would be equal to p mod q, false positive. Right. So I marked another m bed primes that I prefer not to use. Some of them I might have seen already. And it's at most m because in the prime decomposition, maybe the same prime appeared more than once, like divisible by 4. And maybe it has some overlap with the previous set, maybe not. And I'll go and mark, do another shift, mark another subset. I think that you see where it's going. Another set of at most m, which are bed for t of I minus p for some value I, and in this way I generate all the set of bed primes. How many bed primes did we mark like specified in the union of these sets, taking all the bed primes for any particular shift. Each one of them contains only m bed ones. Each shift contains only m bed primes. How many shifts do I have? N minus m actually, but let's say I called it n bed shifts. So altogether, how many bed shifts? Answer is small or equal than m times n. Each set here is of size m. Each set here is of size m, and I looked at n such sets, size at most n. And obviously there might be overlaps between the sets. That's quite likely. I don't care. In the worst case, that's the number of bed primes that I have. How large is pi? Pi is 2 times mn. Meaning that now when I pick a prime at random, it has a chance of 50% that the prime that I picked doesn't appear in any of the sets, which implies no false positive at all. Cool or cool? So if I pick my prime at random, we have a probability which is large or equal than at least half, then I don't have bad primes at all. Okay. So how do we know that pi exists? Let's just skim through it quite fast. How do we choose a random prime in or linear time? The good news is that if you ask how many primes are there as a function of n, as a function of capital N in this case, there is a lot of primes. So remember, I want all my primes to have only m many bits. I want all my primes to be relatively small, at least to fit one computer world. But there is so many primes that it's not hard to generate many of them. Easy to prove that the density of the primes, so there is a lot of primes. And if I'll just pick n to be 9 times m, then the number of primes that I have between 1 to this number, it's large enough. So I can pick, if I'll pick a number at random, from the set and check if it's prime until I'll find a prime, then I'll find a prime quite fast. Since there are so many primes, if you just pick a number at random, don't use any other algorithm, just pick a number at random, ask is this prime or not a prime, and finding if a number of prime or not is, well, your credit card depends on it, and yes, there are algorithms that do factorization relatively fast. or look at a data structure or a database of primes or do the following. Anyhow, just pick at random. And practically what do? You pick at prime at random. The larger the better, but should still fit your computer world, should be smaller than M, should have at most N many bits, most primes will do it, and they are, yeah, just try it. If it works for your data, great. If not, maybe there is something strange in your data, and just pick one again. How many times does it take until you find a prime that doesn't have any false positive? Well, you can either insist on that you can either understand it as there is very low probability that you have good chance of no false positive at all, or you can understand it as it's quite unlikely that you'll have a lot of false positives for one particular prime. So if for every false positive you spend the time to check each element individually, you're good. Understand it either way. Anyway, cool, no? By the way, this paper appeared in the beginning of the 80s, kind of introduced the idea of randomized algorithm, and in the same paper they also discussed an early version of the algorithm of the closest pair between 2 points. So they were two classical problems. Yeah, let's talk a bit about the midterm. I don't know. I'll give you a few questions that I give repeatedly almost every semester, and let's, if you didn't find it, well, already this question in multiple variants I ask in every semester, which is you have a lot of files and find if any two are identical. I like this question. I use it for many years. I use multiple versions of it, and let's play it. Yes, sir. Still about it. Go ahead.
It's about the midterm in general. If you'd like to finish first, I can hold up.
Basically, that's a question. So I was thinking.
Sure. Just to get some more input from the class, I think opening up the discussion to what's the homework schedule looking like? Because I know that my desire to not push it forward is so that we can have more time to review via the homework material for the final. But of course, the conflicting interest is more time to review for the midterm itself. So basically, I'd like to have it sooner so we can have more homeworks between now and the final. If we push it later, are we going to have like a midterm review homework, or are we going to have another homework, or what's the plan?
I publish a few review questions. What I do today. The time of the midterm does not affect the time. It's just more time to. The material for the midterm is the same. It would be everything until hashing. So it's just to have a bit more questions, more time for us to discuss questions. That's essentially the only reasons maybe to give it a bit different. That's the only parameter that is different between doing it now or doing it next Wednesday. And then next Monday will be fully reviewed. But as far as materials, homework, it will be the same. I will not have time, no matter when I publish homework 4, I will not have time to grade and publish the solutions, and I will not try to force people. I mean, the questions will be relevant to the midterm, but you will not see the solutions, at least for most questions, you will not see the solution. Sometimes I'm giving up the solution that immediately just as, why not? We all share the same desire of, getting you, there is no attempt to sabotage your career completely. So material homework, everything will stay the same no matter what the midterm. I will not add more. If we are moving it, I will not add more material to the midterm. Promise. So if it will cause people to change your mind, we can continue on Piazza and let it think. And for my side, I really don't care. Just asking what's the best for you. Yeah, you have a lot of files. I at least have various copies of the same file that I gave with different names, different directory, different, etc. You want to write a function that will tell you here are two identical files. And naive algorithm, not disjoint forwarding, naive algorithm would be check every two files, take every bit on the files, and check if they fit. And various obvious heuristics, if the files don't have the same length, let's make sure that they all have same length, size, sum of ASCII characters, if I'm using ASCII characters. Why do I say that they all have the sum of ASCII characters? Because people tend to think about, let's sum up the ASCII values of all the characters in the file, if it's document or image, and that's not a good hash function, so I'll put it out of the discussion immediately. It's not a terrible heuristic, but as a hash function, it's you can do better. So yeah, how should we do it? Again, slow algorithm, check every two files, and if you suspect that they are similar, they pass your, say, the obvious sanity check filtering. They do have they look like they might be. At some point, you need to check each character independently. Do they fit or not? And finally, the big thing, so it's expensive operation. You cannot avoid it completely, but I mean, you cannot avoid it completely, but you want to make sure that it happens with low probability, that false positives are rare. They don't happen frequently. So not too hard to think about, but somebody should vocalize it.
Can we just hash?
Yeah, obviously it will start by some hashing of each file and comparing the hash value of the files. Not too hard. And in this part, to make it a full answer in the meter, definitely if it's in the homework, then I want to know which hash function are you using. So which hash function are you using? Files are a big thing. And remember when we analyzed quicksort, we had a few steps, and one was let's look at good pivot. That there is 80% chance to find a good pivot. What is good pivot? A key that is not in the 10%, that is the smallest one, not in the 10% of the bigger one. And then the proof went by saying you have 80%, look at the set of keys that you're going to sort right now in this stage of the sorting, and you have 80% chance to pick an element in the middle 80%. Da. And if it does happen, if all your choices are good, then your tree will still have logarithmic height, not log to the base 2, log to the base of smaller number, because it might be that a lot of the elements are here and only 10% are on the other side. But a constant fraction will split into each side of the recursion. So that was one proof. If you don't remember it, ask, or I can go over it, or at least revise it. And the more subtle proof, but harder one, was really going over the backward analysis once again. I looked at two elements, I and j, asked what's the probability that they'll ever be compared. When will this element I and j will be compared? They'll be compared if among the set of I, j, and everything in between, the first element that I picked is I, and then it will be compared to j. As first element that I picked as a pivot was I, and then it will be compared to j. Or the first element that I picked as a pivot was j, and then it will be compared to I. In these two cases, I will compare them. If I picked an element which is between I and j, then they are going into different slides, and I will not compare them. So we asked what's the probability that I and J will be compared. It depends how many keys are there between them. That's the only parameter that determines it. Since I pick a pivot uniformly at each stage. You look puzzled. Should I go over the proof? I missed it. Yeah. So yeah. And then we had this double sum. That's only. Then we had this double sum where essentially we asked what is the sum of 2 divided by j minus I plus 1. Where does this number is coming from? J minus I plus 1, because I was running through all the ij. And where is coming through it very quickly. I was running through all the elements, or pairs of elements. Here is I, here is j. I assume that they are already sorted. And this number over here is just how many elements are there among them. That's I plus 1, I plus 2, all the way to j. This is how many elements you have between j to I. What are the bad choices that will cause I to be compared to j? It will happen if and only if the first one that I picked is either this one or this one. That's why it's 2 over here, sum up into this sum, and I think that I didn't go through the whole procedure. I just said, for a fixed difference of I and j, this element will appear at most n times. For a fixed value of this element will appear n times, and the different values that I have over here are exactly, we have 1, 3, 2 times, and so on, all the way up to 1 over n, which give me a really tight boundary, n to n ln n, which is actually very close to that one. So that was the rigorous part. If you remember all of it, great. If you don't remember, at least remember all the details about the good pivot, bad pivot, and why good pivots are sufficient. Okay, I'm not entirely sure about my weekend plans. There's some family commitments, but when I'm in town, I'll definitely make myself available for questions. I didn't see too much stress to move it. I'll let you meditate on it, but if nobody will say, yes, please move the meeting. If I wouldn't see a few students saying, yes, we are staying with the same date, the same everything. For my format is, some of you took my courses, we'll have 5, 6 questions. You have to answer like 4 out of the 6. Not necessarily with the same grade. If you're getting more than 100, good for you. It's stored and used later for class participation. It's always out of 100. Yeah, I don't know. Zoom people, any questions? Okay. Okay. Thanks. Yeah, I'll definitely be available either Zoom or live on Friday.